Welcome to the second part where we're going to focus more on qualitative analysis. So let's start by doing some analysis and looking again at both the solution curves as well as the phase portrait and direction field for the last example that we just solved. So if you remember, we were solving this this system of differential equations with this matrix. We had our one solution, a complex valued solution. We turned it into two real valued solutions and used that to find the general form of the solution, the general solution rather. And remember that this did look like a spiral going counterclockwise, and specifically it's a spiral that is going towards the origin. It is, so it is a stable equilibrium. You are at the equilibrium, you're not moving. You get bumped a little bit, no worries, you'll go right back. Whereas unstable, right? You get bumped a little from equilibrium and you're gonna go to who knows where, all right? And you might ask, well, how do I know whether we're spiraling in, which way, we're connecting? It looks like we're connecting on the right. Well, the answer is that we're actually spiraling infinitely. So it looks like the spiral kind of ends on the right, but it doesn't. It's recursive in a way. It just, if we zoom in a bunch, oh, this doesn't let me zoom in that much, but it's still spiraling the same amount. And so you zoom in on this, it's actually zooming in is not even going to show you anything interesting because it's recursive. Every time I zoom in, it's going to look exactly the same as before I zoomed in. So just trust my word that the more we zoom in on this, the more we, and you can see, right, when I have different starting values, you can see, right, we really are approaching from all the directions and we'll spiral forever, no matter how much we zoom in. And we can see that by looking at the solution curves as well. So this blue curve I graphed is the x component over time. So for some initial condition, let's say that we start with an x component of 2 and a y component of 1. Then the x component over time does oscillate, right? We look at these solutions, we say, okay, these are oscillating. They have sines and cosines, they're oscillating. But there's also an exponential decay involved. Quite a bit of exponential decay too, right? You see that this decays quite rapidly. So even though it kind of looks like it stops, it doesn't actually stop. If we zoomed in really closely, and I'm not going to do it because I'm going to regret doing it. If we zoomed in really closely, you're going to see it's still oscillating here. It just, again, e to the negative 2t decays very fast. So this is what we have right here. And again, you can think about this as a damped spring. You can think of this as the position, and this is the velocity. Well, they're both going to equilibrium. The velocity is stopping mostly, right? The tiny little jiggles maybe. But yeah, that's what's happening. Stops pretty quickly. Whereas the different spring might oscillate longer. Okay, and again, so we can see this kind of oscillating behavior corresponding to this spiral behavior. Because again, at a spiral, let's say, let's just look at one, right? Let's say we're up here, right? Well, actually, no, let's actually follow the initial condition I plotted. Initial condition of x being 2 and y being 1. So x being 2 and y being 1 is going to be right here. This is the xy plane, not to be confused with the t x or y plane. So this is saying with this initial condition, initially y increases and x decreases. And you can see, yeah, initially y does increase a little bit and x is decreasing quite a lot. And then quite quickly, y starts decreasing as well, x is still decreasing. Yep, quite quickly they're both decreasing, x and y both. And then eventually x decreases enough that x actually starts increasing again. But it never increases, right? X never gets anywhere close to as big as it started. Right, this is how a big x started, an x value of 2. The biggest x gets after that is 0.1. And again, you can see that x started all the way up here. The biggest it ever gets to, hey, about 0.1, 0.09. And again, this is confusing because The first coordinate is the t coordinate. The second coordinate is the x coordinate. X and y ain't what they used to be, my friends. All right, so this graph shows the value of x based on time. Always shifting our mindsets. That's why labeling our axes is so important here. So that's qualitatively what's going on. And again, what do you think would happen if the real part, because remember, this is the real part of our eigenvalue. This is the complex part, the imaginary part of our eigenvalue. What do you think is going to happen if I change the real part of our eigenvalue from negative to positive? Currently, the real part's negative, and we're spiraling into our equilibrium. Well, if I made this positive, what's going to happen? You're not going to be able to see it very well. We're blowing up. Okay. All right. If I zoom out, you can see we get the opposite behavior, right? Exponential growth happens very fast. So these are getting very big waves. And then the small waves are in the past, right? It just changes the direction of time. Just like when we talked about sources and sinks, we said they were the same graph. Just one's going forward in time, one's going backward in time. It's exactly the same here. So if I change this, again, just making all of these negative, I think might do it, then it's the same graph. The arrows just all flip directions, and now it's a source. Now it's spiraling out from the equilibrium. Now the equilibrium is an unstable point. Okay, so that's kind of what the real value, let's change this back. I don't want to look at that. That's kind of like what the real part of these eigenvalues do. And the complex part, right, is that 3. Complex part determines the period. We'll talk more about that in the next video. Let's write some of that down. Let's write some of it down. I'm just talking a lot. Okay. So first, I actually did want to write down how to find the general solution. I got a little out of control. So what is the general solution with complex eigenvalues? How did we do that? We'll get some more practice in this second half. Not in this video, but in future videos. Complex eigenvalues, what did we do? First, we found the eigenvalues. That shouldn't be a surprise. Then we found the eigenvectors. But specifically, we actually only found one eigenvector. We only need one. And remember that when we're doing this, we're going to get redundant equations. And we're going to need the real part, right, to equal, right? We set the real parts equal to each other, and we set the imaginary parts equal to each other sometimes. When you're solving an equation with complex numbers, that is always going to be something that needs to be true. We'll get more practice on that. I don't want to write that down right now. And then we get our complex solution. We only get one solution. We get one complex solution. And then we can use that complex solution to get the general solution. Right? We get the general solution using the real part of that complex solution and the imaginary part of that complex solution. Again, there's no I here, but these are always going to be linearly independent. So that is how we can find the general solution with complex eigenvalues. It's very, very similar to what we did before, honestly, except these are going to be complex now. We only need to find one of them. And then instead of taking two solutions, our two solutions really just come from one complex solution. So it's almost easier in a way. If you squint, it's easier, depending on how comfortable you are with complex numbers. Okay, so this can be a lot, right? Especially if you're not super strong with complex numbers, this can be a lot. We can save ourselves a lot of work because we can do a ton of qualitative analysis just with lambda. All right, so if you don't want to do the whole general solution, you can do a ton of qualitative analysis with just lambda. And that's what we're going to focus on in the next two videos, and then we'll do a lot of examples to get some more practice. Specifically, what do we know about lambda? Let's say lambda is alpha plus beta I. And again, plus or minus. Let's just look at one of them. And we'll say that, well, no, we'll write it in this form. we're going to say beta is positive. It doesn't matter whether beta is positive or negative because we have a plus or minus anyway. So without any loss of generality, let's say beta is positive. That means we don't have to deal with absolute values later, right? For example, what am I saying? I'm saying if this is one of our, if these are our eigenvalues, well, 2 plus or minus 3i is the same thing as 2 plus or minus negative 3i, right? So it doesn't matter whether beta is 3 or negative 3. These are the same two numbers. Okay, so let's just say beta is the positive one. So what can we say about this? What do we know if alpha is positive? What do we know if alpha is negative? What might happen if alpha is 0? Thinking back to our example, right? When alpha was negative, things were decaying. We have exponential decay. They're always going to have this form. We're going to have a sink when alpha is negative. The real part of our eigenvalue. All right, we're going to have a sink. And specifically, it will always look like a spiral. We'll have a spiral sink if the real part of our complex eigenvalue is negative. And again, if beta is equal to 0, then this is just real, and that's kind of boring. Well, actually, if beta is equal to 0, and these are both of our eigenvalues, then we have a repeated eigenvalue, which is not boring. That's the next section, though. All right. And again, what do you think if alpha is positive? Well, it's also going to be a spiral. It's going to look almost exactly the same, but it's going to be a source. All right, it's going away from the origin in this case. What if alpha is 0? What if alpha is 0? Well, look at our solutions. What do you think happens if this part of our solution is 0? Well, then there's no exponential growth or exponential decay. If this is 0, this is just 1 for all time, right? This part is 1 for all time. What happens if this is 1 for all time? Then we have perfect oscillation, right? It's periodic motion. Right? If this is 1, it's hard to see, but if this is 1, right? I could change the orange one too. But if this is 1, we just have periodic motion. Just stays that way. So that's what we have. And it's called a center. The equilibrium is called a center. All right, and we get periodic motion. All right, and specifically, right, these we're talking about the equilibria right now. Or the equilibrium is, and it depends on what alpha is. We talk more about that in the next video too. And just reminder a couple things, right? That our solution, our complex value solution, was e to the alpha t times cosine of beta t plus I sine of beta t. Remember what the periods of sine and cosine are, right? The period of sine x is 2 pi. So let's say sine t. We'll be consistent with our notation. So remember your function transformations or your trig. If you multiply that by 2, it's moving twice as fast. If beta is 2, this is going twice as fast, the period's going to be half as long. And in general, the period of sine of beta t is just 2 pi over b, or beta. All right, the beta is just how much faster does it go. It's a horizontal compression. So the period's getting shorter as beta gets bigger because the oscillating happens faster. So in our example, right, we have beta's 3, so the period's 2 pi over 3. So you can see that, for example, it's kind of hard to see, but really we're starting, if we start here, right, then after 2 pi over 3, we're at the same part of the cycle. And then if we were to like zoom into 4 pi over 3, you'd get to the same part of the cycle at 4 pi over 3. And again, the amplitude is exponentially decreasing. The same like part of the cycle is there. And that's easier to see if it only had a sine component or only had a cosine component, and if the rate of decay was a little slower, because this is a pretty fast rate of decay. All right, so that's pretty much it. I really started sneaking into the next video. We're talking about equilibria, but that's pretty much it for now. Yeah, we'll talk more about equilibria in the next video. Bye-bye.